Hey guys, I'm recording a video for topic 9.4, and as you can see, the title of the topic is resolution. So our learning objectives for this lesson will be to understand the limits on resolution placed by diffraction and to solve problems related to the Rayleigh criterion and resolving power in diffraction gratings. So obviously, we're going to have to define a few of these terms to start. So, resolution. Resolution of two objects is just the ability to clearly see that the two objects are distinct. I have a demonstration that's pretty good for this, and I tried to record it and using video, and I was unable to do that successfully. But you can see this in the wild, particularly I think in car headlights. So you'll notice that when the car is close, you can kind of very distinctly see the shape of the headlight. Or perhaps easier would be taillights. As the car gets further away, the shape of the taillight becomes kind of less and less distinct until it just looks like a blob, a round shape. So you can't tell what the taillight actually looks like as it gets farther away. And so what's happening there is this idea of resolution. So in the case of a taillight, you have one object, although if the car gets sufficiently far enough away, both taillights will appear to kind of merge into one object. Okay, so what's happening here is that light from each of the objects is diffracting as it goes through the opening of the eye of the observer. Remember that your eye is a lens. So the light from each source is going to create its own diffraction pattern on the retina of the eye of the observer. If the patterns are far apart, the observer has no problem distinguishing the two sources as distinct, but when they start getting closer together, that becomes difficult and, in fact, impossible due to diffraction. Okay, so here we can see an intensity graph of two different sources. So we have a red source and a blue source. So this diagram is then going to show the summation of the diffraction patterns. So if we add the intensity of both, you will see here this purple line shows the intensity of both together. Okay, so that is a sum of both intensities. In this case, we still have a clear dip in the center of the pattern, so that indicates that we will be able to resolve the two objects. So you will still be able to tell that you have two different objects in this case. So what is the Rayleigh criterion? Here we have a couple of diffraction patterns from two different sources. In this case, though, they're closer together. And what happens is that the sum of the intensity looks like it's coming from a single source. So in this case, you would not be able to tell your two sources of light apart from each other. We do not have resolution here. All right, so now let's get down to defining the Rayleigh criterion. You can see here we have the central maximum of one source, and this is going to coincide with the first minimum of the other source. And that is kind of the heart of the Rayleigh criterion right there. So the Rayleigh criterion defines resolution in a way such that two objects can be initially resolved where the central maximum of one object's diffraction pattern overlaps with the first order minimum of the other. Okay, and here this line shows that overlapping at a very specific distance. So this specific separation is going to produce a clear dip, a clear central dip and the intensity, even if we add these two waveforms together. And there you see it. So still a clear dip. Note that if we move these guys a little bit closer together, that dip is still going to be there. So the Rayleigh criterion is in fact a little bit arbitrary, and that's okay. We just recognize that it is, and it's better than no criterion, okay? So here we have 3 examples. In example A, you can see that your 2 objects are unresolvable. They appear to be one single object. In example B, our 2 objects are beginning to show some signs of resolution. It's becoming clear that you have 2 different objects here. And in example C, it's very clear that we have 2 different objects. So clear resolution. Okay, so let's discuss the mathematics of the Rayleigh criterion a little bit. Here, obviously we're going to need to define a few variables, but we have here theta sub A is equal to theta sub D, which is equal to wavelength divided by variable B. So theta sub A is equal to the angular separation of sources, and this will be equal to S divided by D radians, where S is the distance between our 2 objects. Theta sub D is equal to the angle of the first diffraction minimum, and B is equal to slit width. Okay, so those are ideas from topic 9.2. And it goes without saying here that we're using a small angle approximation. Okay, so the Rayleigh criterion for circular slits is going to be given by 1.22 times wavelength divided by B. And remember that B is slit width. There you go. Okay, this derivation is not given by the book, and you don't need to know it for IB physics. So don't worry about it. Just know that that's it, and you need to be able to apply the mathematics, which we will do a bit later in the handout that I'm going to share with you. So resolution occurs for circular slits where theta sub A is greater than or equal to theta sub D. So the distance between objects divided by the distance to the objects must be greater than or equal to 1.22 times the wavelength divided by the slit width. Okay, so read your book carefully and get a little additional context if you need to. Diffraction gratings. So we use diffraction gratings because those very narrow peaks that we see are really useful for resolving different wavelengths of light that are very close to each other. Under normal circumstances, this would not be easy. So the resolving power of a diffraction grating will be given by R, which is equal to the average wavelength divided by the change in wavelength. Note that resolving power is going to be unitless. Our units will cancel out. So average wavelength is just going to be the average of wavelength 1 and wavelength 2. So the sum of those divided by 2. And delta wavelength is their difference, so the larger one minus the smaller one. So resolving power is equal also to m times n, where m is the order at which the lines are observed, and n is a total number of slits on the diffraction grating. So therefore, if r is equal to the first thing and equal to the second thing, then those two things must be equal. And that is it. So a very quick lecture. Your learning objectives are to understand the limits on resolution placed by diffraction and to solve problems related to the Rayleigh criterion and resolving power in diffraction gratings. So we've now covered that. Read your book carefully and take a look at Cognity if you need to. And don't hesitate to let me know if you have any questions. You should now attempt to work through the handout. And have a great day.